Let's recall back to when we were doing limits. And I know, you thought we were done with limits. You thought that was a thing of the past. We were on to derivatives and the limits were going to be banished to the ends of the earth. But no, because now that we know derivatives, we can do some stuff about limits that we were never able to do before we had the machinery and the sophistication of derivatives. So I want to return you to a problem where I'm taking a limit and it's some function divided out by another function, and what we get is one of these so-called indeterminate forms. 0 divided by 0, or infinity divided by infinity. Something where we can't just look at it and know the answer. For example, if you have 0 divided by 7, you know that that's 0. If you have 7 divided by infinity, you know that that is going to be 0. So there's all sorts of forms that are known, but some of them, like 0 over 0 and infinity over infinity, we can't just guess based on only looking at the top and the bottom. So how did we deal with this in the past? Well, in the past, we did algebra. In fact, it was a whole bunch of different things. We'd sometimes rationalize, sometimes find lowest common denominators, we'd do some factoring. We had all of these old algebraic tricks to resolve the question of indeterminate forms. Now, what we're going to see in this video is something called L'Hopital's rule. And L'Hopital's rule is like the sledgehammer of calculus. It cracks open a huge category of limits. And indeed, a ton of the limits that we've done in the past, you're now going to be able to do them via L'Hopital's rule quite a bit easier. But more importantly, there's going to be this whole class of limits that we couldn't do in the past that now we can do because of L'Hopital's rule. So let's consider one example of this. I want to consider the limit as x goes to infinity of the function x divided by e to the power of x. Now, if I just sort of think about this naively, on the top, it's an infinity, right? X goes to infinity of x is just infinity. And then e to the x, I remember that e to the x is one of these graphs that's going to also go up to infinity as x goes to infinity. So this really looks to me to be sort of naively of the form infinity divided by infinity. That is my so-called form. Now, if I actually go and graph this, it's going to look a little something like this. Here we have my exponential e to the x, and here I have my linear function x. And they both go up to infinity. But you see how the linear one goes sort of straight up and that the exponential one curves up? It goes off to infinity, but way faster than just the function x. So sort of the idea is that yes, they're both going to infinity, but the e to the x totally dominates just the x. And so it's going to drag it down to 0 way faster than the x is going to pull it up to infinity. Now, I want to try to formalize that process. Here is going to be what L'Hopital's rule tells us. It says that if I have one of these indeterminate forms, the 0 over 0 or the infinity over infinity, that's what we have in this case, then the limit of a quotient of things is the same thing as the limit where I take the derivative of f on the top and the derivative of g on the bottom. And then the hope is that somehow taking these derivatives is going to make the limit easier to do. Okay, so let's see how this is going to work. We have this specific example right here, and what we're going to say is that this is equal to the limit as x goes to infinity. That doesn't change, where I have my functions. I say it's the same thing where if I take the derivative of both of them. Okay, let's see how it goes. Derivative of x is just 1. Derivative of e to the x, this is e to the x. And now what I want you to notice is, when it's written 1 over e to the x, I can do that limit. It's no longer indeterminate. It's going to be a 1 over infinity on the bottom, but it's only a 1 on the top. It's not enough to pull it up to infinity. So 1 divided by very large numbers, very small numbers. I sort of use my shorthand, kind of bad notation, but that's all right. We get the idea that it's going to 0. So L'Hopital's rule has given us something we could maybe look at graphically, a little intuitively, and try to figure out that e to the x grows faster than x. But because of the application of this rule where I take the derivative of the top divided by the derivative of the bottom, we can show it directly. All right, so that was lovely. What happens if we change the x to an x squared now? It's x squared on the top and e to the x on the bottom. And I can bring up my graphs here, and now it's not quite so obvious. This is the e to the x. This is the x squared. They're both sort of turning up towards infinity. Indeed, it's not completely obvious. Maybe it's the case that they cross at some point. Maybe it's that the e to the x always stays bigger. It's not immediately obvious, at least from this little portion of the graph. But we can apply L'Hopital's rule. Indeed, this is saying that we've got an infinity on the top and an infinity on the bottom. They both diverge to infinity. So then, if I want to be able to compute out what this is going to be, well, I can take the derivative on the top and divide it out by the bottom. So this is going to be the limit. As x goes to infinity, that part isn't changing, but then it's a 2x on the top, and divided out, derivative of e to the x is just e to the x, that doesn't change, so it goes to this. Okay, was that helpful? Well, it's still infinity over infinity. 2x diverges to infinity, e to the x diverges to infinity, it's infinity over infinity. However, because it's infinity over infinity, it's still in a determinate form, I can apply L'Hopital's rule to it a second time. So that's what I'm going to do. I'm going to come along here and I'm going to say that this is going to be equal to the limit as x goes to infinity of the derivative of 2x is just 2. The derivative of e to the x, well, derivative of e to the x is just itself, it's e to the x. And now it's no longer an indeterminate form, it's a determinate form. It's a single number 2 on the top divided by something diverging to infinity. That's going to bring it all the way down to 0. So the way I can think about both of these examples is that e to the x dominates the growth of x squared. Yeah, they grow, but e to the x grows way, 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 way faster such that the ratio between them, the x squared divided by the e to the x, it's going to be going to 0, which represents just how fast it is that the e to the x is growing. By the way, this idea that we've done through, you can repeat it for x cubed, x to the fourth, x to the million. If you have x to the million, yeah, you're going to have to go ahead and use your L'Hopital's rule over and over and over and over and over again. But eventually that x to the million is going to get down to a constant, and so it's going to go to 0. So here's the point. E to the x, it dominates every single polynomial you can imagine. X to any power, e to the x is going to grow faster than that. It grows enormously quickly, faster than any polynomial. The standard indeterminate forms are 0 over 0 and infinity over infinity, but in fact there's many of them. Let's consider this one. As long as I think about its limit with brackets of this entire expression, that this is of the form infinity minus infinity. The e to the x, it's going to blow out to positive infinity. The x squared, that's going to blow out to positive infinity, so it's infinity minus infinity. Well, what's that? We don't know. That's another indeterminate form. Now, I want to use L'Hopital's rule, but L'Hopital's rule was about a quotient, an f on the top and a g on the bottom. So what I want to do is a little bit of algebraic trickery to turn it into that form. So what I'm going to say is that this is the same thing as the limit as x goes to infinity. I'm not doing anything there, just changing it around. And then I'm going to take the e to the x, and I'm going to make it like this. X squared times e to the x divided by x squared. You see how I've done this? The multiplying on the top and the bottom by x squared allows me to factor it out, and then I can put a minus 1 here, because if I went and distributed, I'd get the x squared that I have up there. Well, now that I've done this algebraic trickery, what's happened is that we've got something that is applicable to L'Hopital's rule. We've already done this e to the x divided by x squared. We know that it diverges to infinity. That's something we already did by L'Hopital's rule. In which case, this entire thing, all I'm changing this by is subtracting off 1. So this is also going to be going to infinity. And then finally, I've got an x squared out the front here. And this part is going to be going to infinity as well. As x gets large, x squared for sure gets large. So what really is this product? Something going to infinity times something else going to infinity. The product of two things both going to positive infinity is indeed positive infinity. And of course, the key to this was the fact that we'd already done the e to the x divided by x squared. We'd already used L'Hopital's rule. So that this algebraic trickery was really just for the point of making it look like something that we've previously done our L'Hopital's rule to.